In last class we have demonstrated the measurement of moment of inertia of a flywheel. So, in laboratory we have seen the instrument and how to perform the experiment that we have discussed. So, let us now analyze the data and find out moment of inertia and errors on the measurement. So, the working formula for this experiment is I equal to m 2 g h by omega square minus r square divided by 1 plus n 1 by n 2. Omega is basically is angular velocity of wheel. So, angular velocity of wheel and axle the same velocity. So, that omega it can be written as 4 pi n 2 divided by t. So, what is n 2 that you know this just from maximum speed, maximum omega. So, how long it takes time to come to 0 velocity. So, before coming to 0 velocity how many complete rotation revolution. So, that's number is the n 2 and also height can be expressed as 2 pi r n 1 because one round of this turn. Okay. So, that's the if radius is r, then it is a circumference, this is 2 pi r. So, for n 1 turn, so into n 1. So, that will be the basically height because here we assume that after n 1 turn just this mass will touch the floor. So, height one can measure directly or one can find out using this relation because we are measuring r as well as n 1. So, anyway, so here basically our measure ends, the parameters are to be measured basically, that is mass, height h, radius r and time t, including counting of n 1 and n 2. And this, so and the experiment can be repeated for 3 different masses and for each masses 2 or 3 height can be taken. Okay. So, that is in during demonstration I was mentioning most of the things. So, for this experiment what are the instruments are required? What are the instruments are required? So, basically this flywheel, we have seen the flywheel and then weight or mass, then balance to measure the mass or here we have written weight balance or anyway simply balance, then mass, then we need slide calipers, thread, stopwatch and meter scale. Okay. So, these are the instruments we required for this experiment. Now, first as I all the time I mention for any experiment analysis. So, when you are doing experiment, so you have to first determine the least count of your instrument. So, that is meter scale we are using for measuring height or without measuring height using the meter scale also one can find out using 2 pi r n 1 relation. So, anyway, but meter scale whatever we have in laboratory. So, you should know what is the smallest main scale division. So, that is the least count. So, this is a 1 millimeter, that is 0.1 centimeter, and then for weight balance, for measuring mass, the smallest weight, that is 0.1 gram. So, that is the delta m, this one delta h, and stopwatch whatever we will use. So, or we have already used. So, that is the smallest time variation you can detect. So, that is the 0.01 second. So, that is delta t. Slide calipers for measuring radius of axle. So, the vernier constant, you know, this one main scale division divided by total number of vernier scale division. So, 0.1 centimeter by 10. So, this is 0.01 centimeter, that is the delta r. So, all these things first you have to find out and note it down. Then I think this, for this experiment you do not need this temperature, because moment of inertia basically it will not vary with temperature, slight variation of temperature of course. So, but it is always good practice to note down the temperature of the laboratory. So, this in our laboratory its temperature is around 30 degrees centigrade, and then let us first I think noted down the radius of the axle measured by slide calipers. So, make table. So, table 1, this is for measurement of radius. So, we should write down the vernier constant of that one. So, number of observation, the reading of the main scale, vernier scale. So, already you know this, for other experiment I have I think discussed about this table. So, this is the standard table for slide calipers. So, this total reading of diameter is unit is centimeter, and then you have to find mean radius. So, that is basically equal to diameter by 2, it is in centimeter. So, just note down the reading and then find out the mean radius. So, in our case this is the radius, mean radius of this axle is 1 centimeter. So, this is the table 1. Then next this main part of the experiment is basically to this table 2. So, number of revolutions, that is N 2, and time t for different mass and height. Okay. So, this is the main part of the experiment. So, we will take a mass, and that type that we have seen that is it's hanged, this mass is hanged with thread, and then thread is turned around the axle, and how many turns, that is the N 1. So, this then we will release the mass, and then we will start to rotate, and finally, after N 1 turns, after N 1 rotation, this mass will just touch the floor or detach from the it will detach from the axle. Okay. So, via thread it was attached with the axle, now it will be detached. So, then when just it detached, then we have to start the stopwatch, and how much time it is taking to come to the rest, and before coming rest how many turns it will complete. So, that is what we have to count. So, N 2 we have to count, and we have to measure time t, that is for a particular mass and particular height. Okay. So, basically for a particular mass we will take 2-3 height, we will take reading for 3 height, okay. Then we will change mass. So, here what are the columns? Mass. So, we have taken here I have noted down 3 masses. So, one is around 60 gram, then 75, 90 gram. Okay. So, for each mass then uh, this uh, for different height. So, that height h equal to 2 pi r n 1. So, varying the n 1. So, this if I keep 8 turns or and then next 7 turns and then next 6 turn, and for this then corresponding h one can find out because r is known to us, r is 1 centimeter as we found. Yes. So, this 2 pi r. So, this I have noted down 2 pi r here is basically 6.28 centimeter, and then 8 turn, 7 turn, 6 turn. So, corresponding height you can find out. So, for each height, now for this mass, for each height now we have to find out time as well as number of revolution, okay, that is n 2. So, n 2 to find out n 2. So, it may not before coming to the rest we may not have the all complete rotation. So, there may be fraction of revolution. So, you have to, so there he in column. So, complete number of rotation it is say x. So, in our case this for this height is the 8 complete rotation, and then after 8 complete rotation there is a fractional rotation that we have to find out. So, basically this wheel circumference of wheel is 61 centimeter, that you can find out. Just want you take a thread and just round it, and then you measure the length of this that one. So, that is the circumference. So, in our case that is 61 centimeter, 61 centimeter. Okay. So, now after 8 complete rotation, what is the fraction distance? So, this arc you have to measure. So, just again you use thread, okay, and find out this this length. Basically, if, yeah, using meter scale you find out this length of this thread, which is this fractional part, and that we are telling. So, that fractional revolution will be for one complete rotation. So, this is the this 61 centimeter. So, now this you have this part of that is we are taking this length is d. So, d by s, that is y we are writing. So, that is the basically it will be fractional fraction of revolution. So, this d, this part of the revolution is not complete one, 8 is complete revolution, complete number of revolution, and then d, that is the part of that. So, now d by s, so that is y. So, then corresponding y will be 0.63, just you can calculate, and then actually 8 plus this one will be the actual number of rotation. Okay. So, that is into 8.63, and from stopwatch this we have noted down the time. So, that is 25.44. Now, again you repeat the experiment for the same mass, but now n 1 turn that is 7. So, that means height is different. So, then we have taken 3 different height for a particular mass and repeat the experiment. Okay. Then change the mass to the 75 another mass, and then again for 3 different height you noted down the reading. For third mass 90 gram, again for these 3 height you repeat the experiment, and here you will get the for each case for each case you will get the time and time t and number of revolutions, that is this n 2. Okay. So, that is what the main part of the experiment, and after measuring, after noting down this data, now let us calculate the moment of inertia. So, that is the table 3. So, table 3. So, our moment of inertia formula is this one. So, I need to, so in this table there one column for mass m in kg here, okay, and then one we need h height. So, height h. So, this the height column, and then I need n 1 n 2. So, for n 1 for n 2 these columns are there, then I need basically yes time. We have noted down time because we have to find omega. Omega is 4 pi n 2 by t. Okay. So, we have noted down here in this column time. So, from here n 2 and t are available, and using this one. So, this omega in radian per second you have to find out. So, then now g value whatever. So, on top we should write other parameters which you are not is the constant, and other one already is we have measured. So, so this radius we have noted down here. So, from all this data, now for you see this only I have shown here one data. I have other data also, but I have not shown just the same way one can. So, this for 3 mass 3 heights, the same mass 0.06, it is just approximately 0.06 kg. For this mass, what are the other parameters? So, just you note it down, and for this data we have calculated I. So, that moment of inertia is 0.0175, and other also you will get, and then you should take average and find out the average I in kg meter square. Okay. So, this you should write this. So, actually I have all data, and if we take average, so this average will be like this. Anyway, forget that one. Let us say this the our result. Okay. So, this is the procedure to calculate the moment of inertia of a fly wheel. Now, say this is our result. Okay. But actually you have to work with this average one, since I do not have other I do not have shown other data. So, just let us take this the only value we have. So, now error analysis. So, this how to find out the expression for error, that already you are quite familiar with that. So, here I equal to this is the expression, and where h is this and omega square is this one. Okay. So, here h and omega square. So, this we are not measuring directly, r we are measuring directly, n 1 n 2 basically that is count, we are not using any tools. So, there is no delta n is 0, delta n 1 delta n 2. So, this part one can consider as a constant, and of course, mass is there. So, here if I just put the value of h and omega square. So, then m this is 2 g, then h is basically 2 pi n 1 r, okay, and by omega square means this. So, t square will go up, and then 4 pi n 2 whole square. Okay. and this minus r square divided by this. Okay. So, just take out this m r, m is there, r you take out, and then it will this 4 pi 4 pi. So, below 4 pi square is there. So, 1 4 pi will go. So, another 4 pi will be there and into square, and here g t square and this n 1 and then minus r. Okay. So, r I have taken one outside, divide by this 1 plus n 1 by n 2. Okay. Now, in this expression, if we look at this expression, so here r is 1 centimeter as I told this, okay. But here the g value, t value, t 25 point something and then n 1 and divide by n 2 square. Okay. So, this term basically is very greater than r. If it is very greater than r, then we can neglect this r, So, then we can basically write this I equal to m r t square and rest of the things are basically constant, okay, because we have not measured them. Yes, using the instrument. In 1 into of course, we have this is the counting, but just we are not using any instrument to count it. So, we can treat them as a constant, because delta n is 0 in our case. So, this k is basically g by 4 pi n 2. If we just simplify, it will be n 2 by n 1 plus 1. Okay. Just rest of the part is the constant. So, now these are very simple expression. So, it is in multiplication form. So, take the, so this will be this relative error will be added, okay, for each parameter. So, delta I by I equal to delta m by m plus delta r by r plus 2 del t by t. Okay. So, this is very simple now, it is very simple expression for error. Now, just we have one sets of data, just I have put them and yeah, multiplied by I, delta I equal to this multiplied by I. So, we have calculated this error is this one. Okay. So, answer or result is I equal to that was we have seen just whatever I have, not average one, but let us take this average one. So, 0.0175. So, that I can write 17.5 into 10 to the minus 3. Okay. 17.5 into 10 to the minus 3. So, 17.5. So, after decimal is the one digit is there. So, I can keep this error only up to one decimal point. So, this I can write, this one is basically I can write 0.2 into 10 to the power minus 3. So, we have to take in the same format. Okay. So, then basically your error is 0.2 into 10 to the power minus 3, right, 0.2 into 10 to the power minus 3. So, we write in this for 17.5 plus minus 0.2 then into 10 to the power minus 3 kg meter square. Okay. So, this is the way one has to present the experimental data, and one has to calculate the in this case is the moment of inertia, and then error on it delta I, and then result should be written like this. Whatever I got here, so I cannot write plus minus just this way. Okay. So, you should write in proper format. So, that is what I have shown how to write. So, here for error calculation we have simplified it. Without simplification also one can do it directly, but it will be slightly lengthy calculation, as well as yeah, it will looks slightly I think bigger form. So, that I have also calculated like this one, just I will show you, if you wish you can do also. So, I equal to this. So, these are multiplication form if you take. So, this 3 part 1, 2 and this 3. So, delta I by I, delta m by m plus delta of this part divided by this plus delta of this part divided by this. So, this will be 0 because we are taking constant. So, forget this part, this is also fine. Now, we have to work on it, okay. We have to work on this part. So, delta, now here delta x minus y, right. In this case delta x minus y equal to delta x plus delta y. So, summation and subtraction rules we have seen. So, basically this we can write delta of this plus delta of this, okay. And then again this part delta q, if q is a function of x and y. So, you know del q by del x delta x plus del q by del y delta y. So, that is same thing here, your h and omega square is there. So, just 2 g h 2 g h. So, delta omega minus 2 I have taken up divided by delta omega del omega delta omega, similarly on del h, okay. So, this way you proceed, and of course, here this delta r square is there. So, again delta r square. So, delta q. So, del r square by del r delta r. So, just this way one should proceed, okay. And this part, as I told, these are 0 and omega is there. So, here delta omega is there. So, omega, from omega you can find out delta omega by omega, okay. So, it is basically delta omega by omega is coming delta t by t, because delta n 2 is 0. Similarly, h equal to because here del h is there. So, h equal to this. So, from there you find out del h, okay. So, it will come in terms of delta r. So, this you put here in this expression, all this whatever, and then finally, you will get in this form, okay. Delta I by I equal to delta m by m plus 1 by this part is there. What is this? This part this part is there here, okay. And then 1 by this part, and then for this one whatever we have find out using this one. So, that will be 4 g h by omega square delta t by t. So, delta t by t plus delta r by r plus 2 r square delta r by r. So, in this form you will get the expression for delta I by I. So, this also one can use, but it looks slightly bigger expression. So, if you wish you can use this one, or as alternative ways I already discussed. So, it looks simpler, but you have to take approximation, this approximation. So, I think these are all for about the moment of inertia of flywheel, whatever we have studied, basically theoretical calculation means working formula we have derived, and then we have demonstrated in laboratory, and then we have analyzed data and find out the error on the measurement, and report the final result with error. Okay. So, I think I will stop here. So, thank you for your attention.